Assalamualaikum and good morning, everyone. Let us begin our lecture today by the recitation Surah Al-Fatihah. Alhamdulillahi Rabbil Alamin. Ya na'budu wa iyyaka nasta'in. Siratal mustaqim. Siratal ladzina an'amta 'alaihim. Okay, I am Dr. Khaizuran Abdullah from International Islamic University, Malaysia. I'm also the DSP DLT Technical Chair for IEEE Communication Vehicular Technology, Communications Comsort BTS Malaysia Chapter. This is to remind you that this talk is organized by IEEE Malaysia Comsort BTS Joint Chapter and co-organized by CWT MMU with NET UPM, WCSP IIUM, MMU Postgraduate Enrollment, and IEEE IIUM Student Branch. I'm going to be the MC for this morning DLT talk. For your information, DLT or DSP enables current and past distinguished lecturers as well as Comsort officers, IEEE fellows, and prominent speakers to schedule lectures while traveling on business trips. However, because of the due to COVID-19, we are only having in virtual. We are very lucky today to have Prof Ekram. Thank you very much, Prof Ekram, for your time, for giving your time to be with us this morning. Okay, Winnipeg now is at about 9 p.m. right, Prof?
Yes, 9 p.m. 9:05 p.m. Yeah.
Yeah, it's night time, almost to the end of the day, maybe. It's 13 hours different. The time from here to Manitoba, right?
Yes.
Okay. How's the weather there, Prof? Winnipeg?
Very good. Now we have summer, so it's very pleasant. Yeah, it's very nice now.
Yeah, okay, very nice weather. Maybe 27 degrees Celsius?
No, 20 degree.
Winnipeg is the capacity of Manitoba, right, Prof?
Yep.
And then it's about 2,000 kilometers from there to Niagara Falls. Is it?
Yes, you're right.
Of course, we are live at Facebook, facebook.com/combt.org, live videos. Don't forget, all participants can register using the QR scan. All right, you can scan the QR code to do the registration, as well as you can download the slide presentations. Okay. I saw at about 8 a.m. today is about 103 participants registered. All right. So now I see about 118 registrations. All right. I hope there is no bottleneck like the session whereby we have Zooming or for Facebook. I hope the numbers can be more than 100 people. Okay. Alhamdulillah, Prof Ekram was here before in 2013, right? To do the DLT. And then I would like to invite Prof Ekram. Before that, let me say about, or let me cite something about Prof Ekram biodata. The biodata is already in the flyer. Prof Ekram Hossain is a professor in Department of Electrical and Computer Engineering, University of Manitoba, Canada. Prof Ekram is a IEEE fellow, a class of 2015. He's a member of the College of Royal Society of Canada, class of 2016. His current research interests include design, analysis, and optimization beyond 5G, 6G cellular wireless network. He was elevated to an IEEE fellow for contribution and spectrum management and resource allocation in cognitive and cellular radio networks. To date, his research works have received 29,000 citations, Prof. Very good. Google Scholar with Edge index is 89. It's very good, Prof. Very excellent. Okay, Prof Ekram also is a distinguished lecturer of the IEEE Communication Society and the IEEE Vehicular Technology Society. Also, he is elected member of the Board of Governors of the IEEE Communication Society for the term 2015-2020. I think without further ado, I would like to invite Prof. Ekram to deliver the talk. The topic is radio resource allocation in the beyond 5G era, promise of deep learning and deep reinforcement learning. So it's about signal processing communication. More or less, it's about the intelligence system applicable for the cellular communication, right, Prof?
Yes, you're right. Thank you.
So, yeah, please proceed, Prof.
Yeah, thank you very much, Hazreel, for your generous introduction. And
welcome, Prof.
Thank you, IEEE ComSoc and VTS Malaysia to organize this talk. And I'm pleased to hear that there are more than 100 people who have joined this talk. So thank you, everyone. So this talk, as Dr. Hazreel mentioned, about actually intelligent systems, or more specifically, machine learning in the context of wireless communication. So I'll talk about the promises, like potentials of using machine learning techniques in designing future generation wireless systems. So here is the outline. First, I'll talk briefly about the evolution of cellular wireless systems. Like, now we are in the 5G era, right? A lot of research going on for designing 5G systems, and hopefully they will be installed soon, because due to COVID, I think it has slowed down, but hopefully by next year, we'll see deployment of 5G systems. So research has begun for beyond 5G systems. So what some people call it like 6G systems. So I will briefly talk about this evolution. And then I will briefly talk about these techniques, neural networks, deep neural networks, and deep learning, because this what this talk is about, right? So as I mentioned, we will see how these artificial intelligence techniques can be used in the context of designing wireless systems, right? What are the potentials, and what are the problems involved, and kind of which are the future challenges that need to be overcome to use these techniques, okay? And then to give a more specific example, I will show you like how this deep learning and deep reinforcement learning techniques can be used for a simple resource allocation problem in a multi-cell cellular wireless network. And I'll conclude with some, outlining some research challenges, okay? So the evolution of wireless systems, as I just mentioned, starting from these 1G cellular systems, we have evolved through 4 generations already, and now we are in the 5G era. And as I said, research has begun on beyond 5G systems, right? So, 5G systems have primarily introduced new technologies like massive MIMO and millimeter wave communication. So these two are the kind of main technologies that make this 5G, right? The other technologies like heterogeneous networking, D2D, Cloud RAN, they were even in 4G systems, so they're not completely new. But now when we talk about beyond 5G systems, there will be more technologies coming in, like cell-free massive MIMO, visible light communications, drone-based communications. So these new technologies are likely to be integrated in beyond 5G cellular systems. Also, maybe some underwater communication systems, they'll be also integrated with the terrestrial wireless networks. And what is probably even more interesting, softwareization of the communication systems, right? To provide more flexibility, like SDN-based systems will evolve, and also convergence between communications and computing. I think this is like a key kind of aspect of future systems. You might have already heard about this edge computing, fog computing, etc. Right? So those are actually are becoming part of the future wireless systems. They are like part of the radio access network, like edge servers, edge computing systems will be part of the radio access network in future systems. And even like technologies like smart power grid, or what some people say energy internet, are likely to be also working closely with future wireless cellular systems because, these cellular networks incur loss of power consumption. I mean, to run all these base stations, you need lot of power. So they need to be more efficient, kind of, more smart in terms of energy consumption. So they will be integrated with future smart grid systems to have a more kind of efficient, power efficient operation and things like that. So power grids are also likely to be integrated with future wireless networks. So anyway, so what we see from here, the networks are becoming more complicated, more complex, right? And therefore, obviously, as you can assume, the controlling those networks, to manage those networks will be increasingly more difficult, right? And new techniques will need to be developed. Smart, intelligent techniques will need to be developed to manage, control, and optimize these kind of very heterogeneous systems. So this is what I mentioned. So future communication systems will be characterized by these aspects. So convergence between terrestrial and non-terrestrial communication networks. Of course, then we need to provide massive capacity, massive connectivity, and energy efficiency. And also they need to be more flexible in terms of programmability, upgrade, etc. So we will need a more programmable environment, which can be probably done through this SDN concept, software-defined networking concept, and convergence of communications and computing, as I mentioned. So these will be like some of the key aspects of future systems, and all these will bring new complexity into the system, right? And traditionally, I mean, when you want to design a system or optimize, you use simulations, or if you want to do it analytically, generally you solve some optimization problems, right, to find kind of theoretical solutions, to have some kind of idea about the performance and optimal parameters and things like that. But as I said, as things get more complex, those techniques become increasingly more difficult, may not be feasible, may not be useful to solve those complicated problems. I will show you a few examples. So people have started talking about new techniques, and specifically artificial intelligence-based techniques for future wireless systems, for wireless access, resource management, control, security, etc. So basically for future RAN design. Those problems, like RAN design problems, will be more complicated, as I said, because allocation of the resources will involve allocation of both communications and computing resources. It's not only communications like channel and power, but also, like, for example, the edge computing servers, they'll be part of the RAN, as I said. So how do you allocate resources in those edge servers to the different mobile users, mobile applications? So the design problem gets more complicated. And as I just mentioned, traditionally optimal solutions for those design problems have been used by using optimization techniques, genetic algorithms, kind of optimization, and different kind of optimization, combinatorial optimization, which are solved by branch and bound techniques, etc. And these techniques often incur high computational complexity. I mean, you cannot really find the solution online instantly. If you have a combinatorial optimization, I mean, it will take probably months, or even you won't be able to get an optimal solution because it's like too huge, right? So those techniques sometimes become useless. You cannot use them for practical system. So what often we do, we use some suboptimal solutions. We approximate, the problem formulations. We relax some of the constraints, and we use some technique to obtain suboptimal solutions. But those suboptimal solutions again could be really computationally huge. Even though they're suboptimal, they may not be very simple to solve. And also, since they're suboptimal, the performance could be poor, they could be far from the optimal solutions, and sometimes we don't even know the optimality gap, right, between the optimal solution and the suboptimal solution. So there are problems with these traditional techniques when we want to solve realistic, practical wireless design problems, right? And as I said, therefore, people have started talking about using machine learning. So what is machine learning? More specifically, what is like data-driven machine learning? So I just give you a simple example here. Say you want to classify your emails, some like spam emails and some useful emails, right? So you may have a spam detector in your computer, right? So that spam detector can use some machine learning technique. So basically, you have a machine that has to be trained to do certain job, right? Say for spam classification, you have some sample emails, right? Some of them are spam, some of them are valid. So those are like a data, right, that you have. And you use those data to train your classifier, train your machine so that, it can distinguish. So like you give inputs, those samples, and you know, okay, the output, right, is a spam or valid. So using this label data, you can train your machine, So after you train your machine, then you can use it for your, practical application. And then when you deploy the machine, then an email comes and hopefully it can classify it as a valid or a spam email. So basically, this kind of machine is used when you don't know the precise relationship between the input and output, right? So it's like this machine is doing acting like a function. It's taking some input and producing some output, right? Take an email as input and producing output 1 or 0. Is a spam or not, right? But we don't have an exact relationship here. The functional relationship is not completely known. So I mean, if we knew the exact equation, we have an equation, then we can just, plug in, x to f, and then we get y, right? But it's not like that. So, so we cannot really write a code, right, like a program, like an if-then-else code to solve this problem, right? So that's where machine learning comes into play, when the rules are not known, right? You got to design a system with given certain inputs, and you need to produce some outputs, but you don't know the rules, right? I mean, you don't know how to write this if-then-else code. I mean, you cannot write it, right? So you need a machine that can learn somehow from the input data, like from historical data, this relationship, and then hopefully when you deploy the system, it can do the job, right? So basically, this is how a machine looks like. So it should have a training module and a classification module. So as I said, using the training data, you basically train the machine, So you give him some sample data and you tell him, okay, this is the output, right? So I will tell in more detail how this training is done. So the machine kind of somehow learns this functional relationship. It tries to approximate the relationship by a function. Okay. Now after it is trained, then you deploy the machine for your job, right? So and you give input data, and then the classification module will produce the output. So say for image classification, you train the machine giving some images, cat, dog, whatever, and you train it, and then you give a cat, and the machine can say, well, it's a cat, right? So it can produce a correct output. So as I said, the training module is used to train the classifier, and the classification module is basically used to do the classification after the machine is trained. Okay, so all you are doing actually trying to design a machine that can approximate this functional relationship between input and output, which is kind of unknown. It cannot be expressed mathematically, right? Okay. Okay, so as I just mentioned, so with machine learning, the solutions are learned by exploiting the data samples. So use the data samples to train the machine, right? And then you can solve your problem. Now the good thing is they can be used to obtain practical solutions. It's like you don't need to wait for hours to get a solution, right? So after you train the machine, well, it's trained, and then you give input and it will produce the output almost instantly. It's not like a solving optimization for hours, right? So it can produce the solution instantly. So that means it's like a practically useful, right? So they can be implemented online. That's what I said. So implemented online, so you can use them right away. Now, this deep learning is a class of machine learning. Machine learning is a more general term, and deep learning is a subclass of machine learning, which is based on what they call deep neural networks, right? So we'll see how a deep neural network looks like. So deep learning is a class of machine learning. Nowadays, this is like one of the most hot topics. So people are trying to use deep learning in many problems. So this is a special type of machine learning technique that uses artificial neural networks. We will talk about this. Okay, so now when we use these machine learning in the context of resource management in a wireless system, so what does resource management mean? You know, like in a say, cellular wireless system, the resources are like the channels, right? Wireless channels, and say the base station, the transmission power, you know, those are the resources. Now, those need to be allocated among users, right? So for example, when a base station transmits to user, it has to use a channel, right? And has to allocate some power to that channel. Again, in the uplink, say when a user transmits to a base station, it has to use a channel which should be allocated by the base station, and it also has to use some transmission power. So these are like the resources. Now, management means how to allocate those channels, how to allocate those powers. I mean, efficient, not like randomly, right? You want to do them efficiently so that, you know, the total system capacity is kind of maximized, right? So you have an efficient operation of the system. So now, when we think about using a machine learning technique, this means I will need to design a machine, and I will train the machine with some data. Okay, like for example, I tell the machine, well, you have got say 5 base stations, and you have got say 500 users. These are the users' locations. These are the users' channel gain, etc. And you tell me, how should I allocate these? Say you've got 50 channels in total. How do I allocate these channels among these 500 users? Which channel should go to which user, right? So this is like a decision that I need to make. And in each channel, how much power to allocate. So this is like the problem, power allocation problem, right? So your machine will take input those data like users information, users location information, you know, the channel quality information, like for each user, each channel has a corresponding quality, and then it should produce the output, right? So then you get to train the machine first, and then it will be ready to produce your output, right? To train the machine, you need data. So you need to have data. Now, those data maybe you can generate offline, you know, some by high speed computing system. You generate those data offline based on some optimal or suboptimal kind of algorithm, right? And use those data to train your machine, and then you can use it. So that's kind of the idea of solving an optimization problem, right? Using machine learning through some training process, right? And then basically it will do a regression afterwards, you can say. Regression means like it's like the classification module. After you train, then you use it for your problem, right? So the previous example was for classification. Now in this case, it could be like a kind of a regression, or it could be a combination of both classification and regression. But anyway, so there are some main features of this kind of machine learning solutions. First of all, I mean, there is no performance guarantee. So the machine may not be able to generate an optimal solution, you know. So still the solution could be suboptimal, but maybe this is better than other solutions, right? So you may be able to tune your machine, right? You can adjust the parameters of your machine, you know, train it, you know, or change its architecture, etc., to produce suboptimal performance which is better than the other suboptimal method. So then it's something useful, right? Sometimes there is a lack of interpretability because sometimes it produces some output which you may not be explained very precisely because it's not like a mathematical, kind of, there is no mathematical relationship, exact relationship, right? Or the way the machine was trained it is not very, it doesn't generalize well to the data outside the training data and things like that. So I mean, sometimes it could be hard to explain the results, right? But of course, there is some reason, right? I mean, which is still people are trying to discover. I mean, so, but at this point, many of the approaches are kind of a black box approach, which are sometimes unable to explain the precise, mapping between inputs and outputs. So things can happen, but you may not be able to explain very precisely why this is happening. But as long as it works, the solutions are better than existing solutions, then it serves the purpose, right? And of course, as I said, it depends on the availability of data, right? I mean, you need to have data to train your machine. Without data, I mean, if you do not have data to train your machine, I mean, forget about this. I mean, you cannot do much, right? You cannot use this technique, right? So you need to be, have data, right, which maybe from practical system, or you have generated from synthetically, maybe using some optimization models, right? So you need to have those data. So this is kind of one of the main challenges in using machine learning, data-driven machine learning techniques to make data available. Okay. So when do we use machine learning? So there are two cases you can think of. Like, first of all, when there is no mathematical model, for the problem that you are trying to solve, right? Say, for example, you are trying to develop a detection method, a signal detection method for a very weird communication environment for which there is no actually propagation models, developed. People don't know how to precisely model the propagation environment, right? So, I mean, it's not possible to develop a mathematical model to, to find the detection probability or whatever, things like that. So you can use a machine learning model. So you have some samples, right, from that environment. Say, okay, you observe some data. Okay, you give this input, you observe this output, right? So you can generate some label data. Using those label data, then you can design a machine, and you train the machine, and then, okay, you put it for operation, and when the data comes in, it can produce it can tell you what should be the output, right? Or by observing the output, it can tell what was sent, right? You see what I'm saying? So in a weird communication setup, right, you observe some practical data for known inputs, right? You observe the outputs, and these outputs correspond to what inputs, right? Because what you sent, and you observe the output. So okay, if you observe this output, this is like the input was this, right? So from these data, you can train your machine. And now when you use your machine for solving detection, so something was sent, and you see what is observed at the receiving side, and then it's like a classifier, right? So that it can tell what was transmitted, right? So you don't care about any model here. It's just a pure data driven. Or another case when there is no efficient algorithm. As I said, many of the optimization algorithms problems are very difficult. They could be combinatorial, right, in nature, and they are not, I mean, they're easy to solve, right? They take huge computation. So this problem, they call it algorithmic deficit. So even though you can model the problem, but solving the problem is impractical, is like infeasible, right? So you want to use, 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 you want to machine learning, like the one that I mentioned, like solving an optimization problem. It could be a combinatorial, right? So you cannot solve it in real time. So you better use a machine. You use machine learning techniques. So train the machine with your training data, right? For giving inputs, this is the optimal solution, right? So with this labeled data, you train the machine and then you use it, right? So when you use it to solve your problem, you give the data, user information, their channel information, things like this, and the machine tells you how to do the channel allocation, power allocation, right? So it solves the optimization problem, right? Okay. So again, you see, this is like a mapping. With given inputs, it produces the optimal outputs, right? So it's like doing a mapping here. So by training, we let the machine learn this mapping approximately, right? Yeah, of course, you need to, your task should have a well-defined inputs and well-defined outputs. So for this, say, resource management problem, you got to define precisely what are the inputs and what are the outputs, right? And then you need to have data, right, corresponding data to train the machine, and then after training, you can use it. So the function does not change rapidly over time. As I said, a machine actually tries to learn a function, right? Now, if the function changes rapidly, because the training data may not be able to capture all, different variations, you know what I'm saying? So if it kind of very, volatile kind of function, it changes very rapidly, the training process may not be very good. So the approximation may not be good, so you may not get like good performance, so as long as the function, is not like a widely, rapidly varying, right? This would be a good problem to solve, probably using machine learning. A large data set should be made available. And since the solutions are not optimal, they're suboptimal. So, as long as you can accept some error, right? Then you should use it. But if you say no, I want like optimal solution, well, then that's not probably the right tool, because the solutions still are suboptimal. Okay, so let's give a quick example like of this issue, like algorithmic deficit. As I said, some problems you can model, but they're hard to solve, right? So this is a simple resource allocation problems, a sub-band and power allocation in a multi-cell network, right? So you've got, say, K cells, right? Total, as I said, say 100 cells, right? And you have got, say, 500 channels, right? And each cell has a power budget, like each base station has a power budget, right? And each cell has a number of users, right? So say you want to find the optimal allocation of those channels to the users, right? In this entire network, right? If you want to solve the problem entirely, like on a global basis, so that you can get probably the best performance, right? So how do you do? So the problem, if you put simply like this, say, utility maximization. So you want to maximize the total rate, total capacity in the network. So that's what your total capacity, right? That's your total capacity in the network that you want to optimize across these K cells. In each cell has these UK users, and all these channels can be used in all cells. It's like a universal reuse, right? All channels can be used in all cells. So this is basically the objective function, right, that you want to maximize. And of course, you have some constraints like the total power constraint, right? Like this. So the optimization will look like this. But you see, even though it looks like a simple optimization, it's basically a non-convex combinatorial optimization. This is a non-convex combinatorial optimization problem, which means, it will take years, to solve it even for a simple setup. Say, for example, you have got, say, only 15 base stations. You have got 5 channels, right? And you have got, say, 5 different power levels for each channel. So if you want to solve it really in a globally optimal fashion, you got to check all, you see, look at this number, these different combinations. If you want to solve by an exhaustive search, right, you want to find the really the globally optimal solution, then you see you have to search that many combinations. Think about this, infeasible, impractical, forget about it, you can do it, right? This is actually only for channel allocation. If you do power allocation, then it's even higher. So you see, this is a huge, this is kind of the order of complexity, so this is huge. You can use this technique to solve this allocation problem. So you see, this makes sense to use some machine learning technique here, right? Of course, if you have some data available, right, to train your machine, I mean, you can solve this kind of problem using machine learning. We have an algorithmic deficit here. Another problem here, another example here, say user association problem in an interference channel, right? So say for example, you have got K transmitters and M receivers, right? And each transmitter can serve one user, but one receiver can be served by, say at most M transmitters. And there is a minimum rate constraint for each user. So, so this is basically the signal to interference plus noise ratio for a user who is served by transmitter K. Okay. Now you see, this is an interference channel. So everybody interferes. All transmitters interfere with each other, right? So the question is, which transmitter should transmit to which receiver, right? So how should the receivers associate to the transmitter so that the total rate is maximized? Okay, because you see the channel quality can vary, right? So between the transmitters and the receiver. So if I associate to one transmitter, maybe the channel is not as good. It could maybe do better if I associate to another transmitter. So the association will affect the sum rate. And as you can see, the problem, I mean, can be written something like this. So this is the way you would do it traditionally, right? So solve an optimization, like formulate an optimization problem like this. This is like the total sum rate. And you are looking for this association variables. These are the vector that you want to find out, right? So these are the constraints, right? This is like the minimum rate constraint. And the optimization variables are binary, right? They're 0 or 1. So as you can see, this is a combinatorial problem because this is like an, because you get to see all possibilities because the association is like a binary association. So this is like a combinatorial problem. I mean, you get to check all possibilities, like which transmitter should transmit to which receiver, right? And all different possibilities need to be checked under all these constraints, okay? So this is a non-convex kind of combinatorial problem again. And you cannot really get the optimal solution in real time. I mean, for a large system, it will take huge time to solve it. So often what you do, you will relax this constraint maybe. So instead of making it binary, you make it continuous maybe, right? Relax. So you basically relax this constraint. So you can get a kind of a suboptimal solution for this problem. So you cannot solve the original problem, due to the complexity. Okay, so again, you have an algorithmic deficit here. I mean, this kind of problem you can solve using machine learning. Now you see, this becomes more complicated if you also do power control here, because this is only the association, but you may also want to do power control, like this transmission power for each transmitter can be also adapted. It's not only association only, but you can also do power adaptation by the transmitters to maximize the sum rate. So the problem gets really complicated, even more complicated. So when your optimization involves the power variables as well, okay? So that you can solve in real time. Okay, so for a large system. Okay, so anyway, so machine learning has been used for wireless communications. It's not new actually. So starting, for physical communication problem, as well as for like a higher layer problem like mobility prediction, hand-off management, people have been using those. But those are more like traditional techniques. Recently, however, more emphasis has been on deep learning techniques, as I mentioned before. So instead of using those traditional techniques, people are trying to use deep learning techniques like deep reinforcement learning and supervised deep learning techniques to solve this problem, because in general, deep learning techniques can provide better performance. They can handle huge data set, and they uh, can extract more features and things like that from the data. So there are advantages of using deep learning compared to traditional machine learning techniques. So I just to give you a brief idea about these different machine learning techniques. There are three major categories: supervised, unsupervised, and reinforcement learning. So the one that we have been talking so far, they are all like supervised learning, because you have some data, and then using those data you train the machine. But they're also like unsupervised learning, where you don't have data. So they are used basically for applications like clustering, right? You have got some data and you try to find clusters within the data, like data of similar types, right? So you want to do learning, on those unlabeled data, right? So those are like unsupervised learning. And another category is reinforcement learning, where you don't have data. So that's why you want to learn by interaction with the environment, So that's really a good one, because it avoids the need to have data. You don't need data if you want to use reinforcement learning, okay? So I think I have already talked about the supervised learning, so I won't talk again here. And supervised learning, there are the different types, but the one that is of our interest now is neural networks, because deep learning, as I said before, and deep reinforcement learning, they are based on neural networks. Okay, so the neural networks are the building blocks for deep learning and deep reinforcement learning. So a neural network actually is something that looks like this. It's like a bunch of what they call these elements called neurons. So there are some like processing units, right? These neurons organized in multiple layers, and like output from a neuron goes to inputs to the other neurons. So what do they do inside? What does a neuron do? So it does some processing on the input data. Say, for example, if you take these neurons here, neuron here, right? So it takes input from, say, these are the inputs here actually. So these say M inputs. So it will process those inputs. So what does it do specifically? So what it does, it basically does a weighted summation. It does a weighted summation of the inputs, and then it can add what they call a bias value. And then these output can be passed through what they call an activation function to produce the final output. So what does it do actually? So a neuron can be used to like approximate like a function, you can say. So if you give some inputs, it produces an output, right? So it kind of represents a function actually. So now if we train these neuron, like training means finding these weights. If you can find these weights properly, we can represent a function by this neural network. So let me give an example. Say this one here. So this is like a how many neurons you have here? You've got two neurons here and one neuron here. So you've got three neurons here. So this is a neural network that is used to approximate an exclusive OR function, for example. You know this exclusive OR. So this neural network approximates an exclusive OR function, right? So an exclusive OR has two inputs and one output, right? So these are the weights. So if you can choose the weights properly, this will implement this exclusive OR function. That means if you put, say, 1, 0, the output will be 1. If you put 0, 0, it will be 0. If 0, 1, it will be 1. So it will be representing the function exactly if you can train this network properly, which means you find this weight and these biases. So these are the values that need to be obtained. And this is what is called training. So by training means obtaining these values, okay, so that you can approximate the function that you want to represent by this neural network. So how do you do this training? By using some data. Okay, if you put 0, 0, your output should be 0. If you put 0, 1, it should be 1, 1, 0, 1, 1, 1, 0. So these are like your label data. So first of all, you initialize these values randomly, maybe, right? And then you will update these values, right? By observing the errors, right? You put some value and see for 0, 1, you find something like, say, 0.4. So it's not like a 1, right? So you see the error here. So this error, by observing this error, you will be able to adjust these values, right? So you put some data, it propagates forward and produces an output, and you see the error, right? The actual output, the ground truth value, what the output should be, and what this is producing. So the difference is like the error signal, right? So this error signal will be propagated back to the network to adjust this value. So this is what they call back propagation neural network. So you can, you have got 4 data. So you basically, do 4 passes, right? You do 4 passes of back propagation, and you try to, find good values for this weight. So this is the learning process, okay? So this is all what is written here: feed forward and back propagation neural network. So that's what it is. So the data is feed forward, and then when it produces the output, the error signal is back propagated to adjust the weights. So that's why it's called back propagation neural network. Okay, so now deep neural network is a network where you've got multiple hidden layers. They call hidden layer, right? Instead of just input layer, one hidden layer and one output layer, you put multiple hidden layers. That's called a deep network. That's it. So instead of one hidden layer, you have got multiple hidden layers. And as I was mentioning, with multiple hidden layers, in general, you can have better performance. Like your error rate could be less. So it improves performance at a faster rate when the dimension of the training data increases. So that's why people are more, kind of more interested in using deep neural network, because they work on huge, higher dimensional data, right? And in general, you can have better performance in terms of the classification error or regression error, okay? So, I mean, that's kind of very high level, description of a neural network. And then you come to reinforcement learning. As I said, in reinforcement learning, there is no data. So the agent, like the decision maker, has to learn by interacting with the environment, right? So the most popular, I show you the, okay, I don't think I figure here. So the most popular reinforcement learning technique, they call it like a Q learning. So Q learning is like learning what they call like state action value. So the system, evolves through certain states, and in each state, the decision maker has to make a decision, right? So if you can define your system in terms of states and action, right, then you can use a Q learning technique. Say, you want to find out in certain state what action to take. So Q learning means learning that decision, learning that policy, So you have a table, like a 2-dimensional table, state and action. So multiple states and multiple actions. So in each state, which action to take, the best action that you want to take, right? So that table has to be learned. Okay, so Q-learning involves learning that table actually. And after you learn that table, you just use it like a lookup table, so, and you learn that table by interacting with the environment. Okay, so that's kind of the high level idea of Q learning. So by Q learning, you learn the optimal action uh, value function. So in a certain state, if you take certain action, what is the optimal action value? You can think of like a optimal utility, due to certain action in certain state. So that Q table contains the optimal action values. So after you learn that table, you can use this. Now, I will not probably discuss the details. This is the equation that is used actually, the Bellman equation, to update those Q values. Because as you learn that table, right, the two-dimensional state action table, so you take some action and you observe the reward, and then you update the Q value using this what they call Bellman equation. So after a while, there will be converging. There will be no change in the value. So that's when you are done with learning. So your table is complete. So basically, you are done learning. You can use the table. Now, this becomes problematic when you have got a continuous state, for example. If your state is not discrete, or you have too many states, then is really not useful to use simple reinforcement learning. And then you use what they call deep reinforcement learning. So in deep reinforcement learning, that action value, right? In a certain state, you take certain action. What is your payoff, right? That's what we obtain in the Q table. Now that action values, are approximated by a neural network. So this is how a deep neural network looks like. So you have a neural network, right, that acts like an agent. It's like a decision maker, right? So basically, you give a certain state, and the neural network will produce the state action value, like like the values for payoff values for different actions. So okay, this for which action produces the highest value, highest profit, highest benefit. So that action you will take. You take that action, right, which produces the highest utility, right? And this neural network produces those assay values, the state action values, right? Given a certain state for different actions, what would be those Q values? So these are produced here. You're not using a table here, but you are using a neural network, to approximate this function, right? So you give S, and it produces the Q value, right? The QSA value. So this is the idea of using deep reinforcement learning. Here there is no training, like no data or things like this. So the machine has to learn by interacting with the environment. So it takes a decision and sees the reward, right? And then it will adjust, basically, it will learn the policy, by interacting with the environment. So yeah, so that's what the motivation of using deep reinforcement learning. So here I think is a nice figure that shows the difference between Q learning and deep Q learning. So in Q learning, as I said, you're basically learning a table, right? So you have a two-dimensional table, right? So for a certain state, if you have got different actions in the column, maybe, so you have a value, right? So state action value. So if you give state in action, the table gives you the Q value, right? So if you're in a certain state, you see for which action you have the highest value. So you will take that action, right? So this table is learned gradually, and after you have learned, you can use this table, right? But in deep Q learning, you give the state as input. So in our context, what is the state? The state could be for example, the SINR values for different users, maybe, right? So after you do power allocation, maybe, you observe, the SINR for the different users. That's like a state of the system. And then for this state, the neural network produces these different Q values for different actions. So like one idea would be to choose the action which has the highest Q value, right? So basically that's better than other actions. That means that action will be better than other action. So this is kind of the high level view of a deep Q learning. Okay, so folks, I think I have given you kind of a high level idea of this DQL. Now we give this specific example, like we are in part 3 now. So how do you use this deep learning and deep reinforcement learning for this multi-cell power allocation problem? So remember, we talked about this downlink network with K cells and F subbands. So what we will need as well as input, like to the machines to train the neural network for the DL case, the user's channel information. So say in a cell K, right? In a cell K, you have got a bunch of users, and for each user, the channel qualities, you have got like F channels. So for each user has a channel quality value for each channel, right? You have got 3 channels, right? And you have got say 5 users. So for each user, you have got 3 values, right? For each channel. I mean, 1 value for each channel. So you've got 15 values. So these are like the CQI values, the channel quality indicator values. And also for each user, we'll have a location indicator, right? Whether it's a central, in the center of the cell or at the edge of the cell. Okay, so like this could be the CQI vector, right, for a 3 channel, right, for a 1 user, and this is location indicator. So if you've got 5 base stations, 5 users per cell, and 3 frequent subchannels, these are input size. So these many inputs will put as input to the neural network, like in the DL, right? So those will be the input, and the output will be, say, for example, a channel allocation. Like you have got how many channels? Like 3 channels. So in each cell, each channel goes to which user. This could be an output. So I will show you a sample output, like for example here. So the output of the neural network could be something like this. So you have got this is for 1 cell. So you have got 3 channels, right? So you've got 3 channels. So these output could be like this, like the first channel goes to user number 3, second channel goes to user number 5, third channel goes to user number 2. And the power allocation could be like this. In the first channel, you put a power level 1. In second channel, you put power level 2. In third channel, you put power level 3, right? So this, now you can convert to binary, right? And also the complement. So these many outputs, we need for each cell at the output of the neural network. So, and which output means what, right? So this output, for example, means what is the power allocation in the first channel. And this is the power allocation in the second channel. This is, this is the power allocation in the second channel. This is the power allocation in the third channel. This is like the user allocated in the first channel. This is user allocated in the second channel. So the output of the neural network, by observe this output, what those outputs mean, right? So you have to define the inputs and outputs like this, right? And after you define the inputs and outputs, then you go to train the machine, right? You need data to train the machine. So you are designing a neural network, and you have defined the inputs, you have defined the outputs, right? And now, you have to choose, okay, how many hidden layers you want to use, and how many neurons in each layer. So things like those, you can trial and error. You can choose whatever number you want and try, and then you need your data to train the machine. So basically to set up, to find out those weights and biases for the neuron. So anyway, so you can use, MATLAB toolboxes actually to set up your network and just, use your data to train it. So now you use the routine approach. I mean, there is nothing, fancy here. As long as you define the inputs and outputs properly, then you can basically start training your neural network. So this is basically a supervised DL approach, right? Now, to obtain the data, actually, folks, I'll take probably 10 more minutes at best. Sorry about this. So to obtain the training data, like what we use some offline methods, say using genetic algorithm. So using genetic algorithm, we produce some kind of good data. Some sorry. So we use this offline method like genetic algorithm to produce these data. Now you see they are not optimal data, but they are kind of suboptimal. As you can see here, they can be produced at much less effort, like much faster than by doing exhaustive search. So even for this simple system with 5 base stations, and 3 channels, right, and 3 power levels, it takes huge time. You see, like to obtain the optimal data by exhaustive search. You remember the optimization problem, right? So if you want to do exhaustive search, this much of time you need. But using genetic algorithm, you can generate those data much faster. And they're not too bad. It's the accuracy of like 85%, right? So they're not too bad. So they are like, kind of suboptimal data that you'll be using for training the neural network. Well, so here, I show some results, like in terms of configuration of the neural network. Like we use, say, 3 to 4 hidden layers, and we see, okay, so the accuracy could be, as high as 85% here with this. But increasing the number of layers may not be good. Sometimes, it will reduce the performance. So you see, you got to engineer your system, like by trial and error, kind of. By doing trial and error, you got to find your optimal hyperparameter configuration. Okay, and also training samples. Sometimes using too many training samples causes what is called overfitting of the model. When you have too few, it's like the model could be like underfitted, but you have too many, then it could be overfitted. So you got to engineer a system properly by trial and error. Okay, so I think that's about the DL approach. So we see 86% kind of accuracy, which means the solution that the DL approach produces is like 86% of the optimal solution. So it's not too bad, you see. So it's like a quite, like an efficient solution. And as you see, we can produce the solution right away. We don't need to solve an optimization, wait for days, weeks, right? Okay. Now we go to the DQL model, deep Q learning. So now you don't have any data, right? So, the agent will be learning by interaction with the environment. The same system model, same neural network, right? We have a same neural network and with the same number of inputs, right? So you see, in this case, the state is basically what? The state is defined here by the same things, like the number of users and their CQI values and their the location, right? So the same as we did for DL approach. So these are like the state that goes as input to the neural network, and the neural network will produce what? Those QSA values, and then the action will be based on those QSA values. Now, this is like a standard algorithm that we use here, deep Q learning with experience replay. Okay, so this is a standard DQL algorithm, so I'll not probably go into the details. And to benchmark this DQL approach, we again use genetic algorithm-based solution to benchmark the DQL model. So these are the details about this experience replay algorithm. This is like a standard algorithm you can find, like very standard, you know. So to evaluate the performance of this DQL model, we will compare against with a few other schemes. So one is, okay, random power allocation. So now we are not doing the channel allocation here. We are just solving for power allocation. You got a bunch of channels, a bunch of users, right? And you know which channel goes to which user, but how much power to allocate in each channel. That's what you're trying to solve here. And this is another approach, a distributed approach for sum rate maximization under power constraints. So we basically benchmark against a number of these approaches. So again, I mean, what probably the main observation here, you see, this is your optimal, the purple purple line is the optimal solution, which is like a 1, but the DRL one is the orange one. You see the orange one, the orange curve shows the DRL performance. So which is like, you see, is very close, almost like 99% optimal here. So as you know, this shows like for different training samples the error, right? Or you can say the throughput here and error is here. So error is about 1%. The orange one is the DRL on the right figure. Orange one is the DRL, and the other approaches like the max power approach and the random approach, so they are inferior. So on average, their performance is worse than the orange one. You know, so this orange one shows the throughput. So basically, the DRL approach produces throughput which is 99% of the optimal throughput. You see, so it works here. You know, so that's what I said. I mean, you can engineer your system. You can kind of tune your hyperparameters in the neural network to achieve a very good suboptimal performance. Again, this shows the effect of some of the parameters. Like here, again, here on the right-hand side, the number of hidden layers. Like with 2, you get a good performance. But if you go beyond this, so the model becomes like an overfitted kind of. So it does not generalize well, you know, for samples which are outside. I mean, it kind of becomes less general, right? So with more hidden layers. So I think I probably stop. I mean, use my last slide here. So to summarize, the main lesson here is this. ML-based techniques are actually suitable to address complex wireless problems, you know, say resource allocation in massive networks. Too many, you know, many base stations, many users, many channels. You want to do a kind of a optimal, you know, resource allocation. I mean, you don't not just do resource allocation for a single cell, which we have been doing traditionally, right? It's not a single cell anymore. You've got tens of cells and hundreds of users. So you want to do a more global resource allocation. So it's a big resource allocation problem, which is difficult to solve using traditional techniques. So machine learning is a promising technique. And in many cases, you know, you cannot even model the problem. So you may need to use data-driven machine learning to solve those problems, which are even difficult to model, right? With very complex, you know, dynamics, you know, I mean, it's hard to model those systems even. So for difficult problems, ML techniques can be used. And of course, these models are very actually problem specific in the sense that they have to be optimized, like they have to be customized for specific problems, right? And for many communication problems, you can use these DRL techniques by leveraging the state-of-the-art DRL techniques. In the machine learning community, they have come up with a lot of techniques, so we can leverage them for our communication problems. And as I mentioned a few times, the optimal configuration of the DL model is like a fundamental challenge. There is no formula. There is no like a hard and fast kind of rule, or I mean, this is all like a trial and error. So coming up with optimal configuration architecture is more like a fundamental problem in designing machine learning techniques. And potentially, there are a lot of opportunities to, develop these ML techniques for communication problems. And even we can contribute toward the theory of machine learning. In the course of developing those models, I mean, it's possible to contribute to the machine learning theory, for example, to come up with new architectures, probably for communication problems. So they will be a fundamental contribution toward the machine learning theory itself. Okay, so thank you very much. I think I stop here. Hazreel, so sorry I took a longer a bit. So now you guys can ask me questions. Oh, I can hear you. You're muted, Hazreel.
Okay, yeah. All right. Okay.
Yeah.
Okay. Yeah, we have
yeah, I see the question.
two
Yeah.
questions. Maybe you can answer this question, Prof.
Yeah. Well, I mean, this is true for all technologies. I mean, if a technology is not used with care, it can cause problem, right? I mean,
yeah.
we develop
Prof, your video is off, I think, because we cannot see you. Your video. Maybe you can turn on the webcam.
My webcam is on.
On?
Yeah.
Oh, okay.
Maybe it's dark. Okay, let me turn on the light here.
Oh, yeah. Oh, yeah. Because the outside is already dark. Okay, fine. Oh, very good. Got it.
Yeah. Okay. So,
okay, Prof.
I mean, as I said, if any technology, if it's not used with care, I mean, it can cause problem, right? I mean, so it's true for all technologies. I mean, 5G, of course. I mean, there could be issues if you use a very dense, deployment and a lot of kind of EM radiations. Of course, that can cause a problem. But the point is, we need to use it. I mean, probably we need to take this into account during the deployment of the network and things like that. And of course, one of the research is to how to reduce those powers, emissions and things like that, right? So, I mean, but there is no actually clear evidence that this is a threat. I mean, I think this is people are just, I mean, this is kind of overreactions, I should say. I mean, why 5G should be, like specific threat? Why not 4G? I mean, they all have a similar kind of, I mean, they are kind of similar technology. Why 5G is more dangerous than 4G? I mean, there is no really clear evidence, I mean, I think people are kind of overreacting. But as I said, I mean, every technology, if it's not used properly, I mean, it's not used without, kind of.
Yeah, maybe because Prof, people are concerned about the radiomagnetic from the 5G station.
So it's not. I mean, many devices emit radio. I mean, like any electronic device has this.
Yeah. Right?
I mean, so any electronic device can cause long term. If you use something long term, I mean, that may cause problem. But as I said, I mean, without proper experimenting, without proper scientific evidence, it's hard to comment. I mean, you can talk high level, but there need to be studies. I think it's very important as well. I mean, it's important to study and to come up with scientific evidences. But before there is any evidence, I think it's not proper to comment, right, Hazreel?
Yeah.
I mean, my
Because
comment
of
will be
course,
baseless. I
the
mean,
research about this is going on
exactly.
about the
So,
radiations, the level of radiations, Prof. Yeah.
yes, so I think this is a research question, and people, I think, trying to, I think, work on this as well, especially in health sciences and
Fine.
biomedical. So without clear evidence, I think it's not proper to comment on. I don't think we can comment on this.
Prof, I think we have next question.
Yeah.
I think there is one question regarding the hidden layers. How many hidden layers can a network have at most? I think he's considering about deep learning, maybe, Prof.
There is no limit. There is no limit. It depends on your system, right? So there is no limitations of how many hidden layers you can have or things like that. But you see, for your system, maybe 4 layers, 5 layers is enough. You don't need 10 layers. You see, as I said, intuitively, if you put more hidden layers, your function gets complicated. So you have a kind of a more, like, what should I say, overfitted model. You know what I'm saying? So more layers means is like a overfitted model. So your function approximation becomes like a complicated. You know what I'm saying? So it may not be, it may not be general enough. So it may lose generality. So that's why if you increase the number of hidden layers, the errors may go up. So
but
it's like,
is there any mathematical model or anything that to indicate how many layers, Prof?
No, there's no mathematical. So it's all, it depends on your system, your specific system, and you got to find out by yourself by iteration. It's a design process. It's like a design process. So you got to change and see how your errors change and things like that. There is no formula or things like that.
Okay, Prof. Can we go to the last question, maybe, Prof?
Yeah.
Do you still have time, maybe, Prof?
Yeah.
It's already over 20 minutes over 11.
Good question. As I said, 5G has two major technologies actually. One is passive MIMO and millimeter wave. They are the two main, actually, I should say, two main technologies that have been added to 4G to make it 5G, right? So it's still a WaveDM system. So many of the infrastructures will stay the same, So major changes could be in the base station side. So you may have some new 5G base stations which have more antennas. You see what I'm saying? So to accommodate massive antennas. So more changes will be on the base station side, I should say, if there are changes. But on the cell phone side, I mean, you may have new interfaces for millimeter wave and things like that. You see, so millimeter wave and massive MIMO, these are the two major technologies. And on the network side, you see, so those are not standardized. I mean, it depends on the manufacturer, and they don't reveal exactly, what they are doing on the network side, right? I mean, there's something proprietary, right? We don't know, right? So whether they're using SDN, well, of course, these SDN standards, like, those are open standards, but they will be also used in probably 5G infrastructure, right? But exact implementation, well, it depends on the manufacturers. So maybe in the 5G infrastructure, they'll be used the SDN ideas. You know what I'm saying? So SDN controllers could be used. So, but they have been used in the internet for some time anyway. So they're not completely new, right? So, but they are going to be used in the infrastructure of these cellular systems. But on the wireless access part, this is more the millimeter wave and massive MIMO.
Can you answer this question, Prof? This is a long question. But the time is approaching 10:30 over there, right, Prof? Is it 10:30 at night? Is it okay, Prof? One more question?
Of course, I did not say you cannot rely on relaxation. You can rely on relaxation. You get suboptimal solution. Sometimes you get bounce. I did not say you cannot get solution. You can get solutions, but what I'm saying, you end up again with some suboptimal solutions. Maybe with machine learning, you can get a better suboptimal solution. That's what I say. With machine learning, you may get a better suboptimal solution. sometimes relaxation, you only get the bound, right? Even not the solution, you get a bound, right? So, of course, there is no general result that shows that, okay, you can outperform this, but depending on the problem, right? So, you can check, say you design your machine learning method and you can check against other traditional methods. And as I said, you can tune your network, your machine, DRL or DL, to basically produce better performance, probably. You see what I'm saying? But of course, there is no general conclusion. I mean, I'm not saying, okay, in all, you can design your network very poorly. I mean, it can be like a very bad performance, So, but you can also design your network to have probably good suboptimal performance.
Yeah, Prof. I think there are many questions, but we don't have much time on this, Prof. I provide them with your email, Prof. Is it okay, Prof?
Of course, yes, sure.
Ekram.Hossain at umanitoba.ca.
Yeah,
I
you're
already
right.
put in the comments. So
Yeah.
maybe they can forward if there is any question to you. Is it okay, Prof? So here is already Ekram.Hossain at umanitoba.ca.
You're right. Yeah, you're
Yeah.
right.
Of course, if the participants or anyone would like to have the extension of research with you and do some collaborations, they can do so, right, Prof?
Yeah. I mean,
Yeah.
I can
Okay.
I can try to help as much.
Yeah, inshallah.
Yeah.
Okay. I think that's all for today, Prof. Times there is already 10:30, right?
Yes, you're right.
Right,
It's
Prof? Is it
10:25.
correct?
Yeah, 10:25. Yeah.
Yeah, 10:30 at night, so it's already late.
No,
All
it's
right.
okay. Yeah.
So thank you for your time, Prof.
Yeah,
Thank
thank
you
you.
for
So
the
I hope,
sharing
I hope.
slides. Okay, of course we have a lot of
Yeah. Hello.
yeah.
Yeah. Yeah. So
Hello,
I
yeah,
hope,
yeah, yeah, Prof. Really, I can.
so thank you again. So I hope the talk was useful. I mean, at
Yes,
least.
very useful. Yeah, very yeah.
Okay.
Thank you
Yeah,
very
but
much.
the time is limited. I mean, there are a lot of things to talk about, but I mean, unfortunately, So next time we'll talk more, maybe. Hazreel, yeah.
Okay.
Yeah.
And we want you to be here physically, Prof.
Yeah.
Because of the coronavirus, that's why.
Yeah. Things have changed.
So I hope you happy with the situations. I mean, delivering your speech via the virtual. I hope next time it can be available physically in Malaysia, inshallah.
Yeah, of course. Yeah, sure. Yeah. Thank you all. So
Okay.
have a good day.
Yeah. Thank
Yeah.
you. And then don't forget our participants who are here, please join to be the member of IEEE Comsort. You can do so at www.ieee.org. Okay.
Yeah, and
Yeah,
Hazreel,
Prof.
I just want to mention one thing. Like due to this COVID thing, IEEE has Comsoc has made all the magazine kind of open now for all
Yes.
Comsoc members. So you can access any article from the magazines until
Okay.
August 15. Any
Yeah.
Comsoc member can access. So it's like an opportunity to probably download and read, some of these articles, from if
Yeah.
you do not have access to Explore, but if you have Explore, you can get. But if you do
All
not have
right.
access to Explore, still you can download those articles. They're open now. Okay.
Okay. Thank you
Yeah.
very much for your info, Prof.
Yeah. Thank you.
Okay. See you later. See
Yeah.
you
See you
all.
later. Take care.
Okay.
Yeah.
All right.
Take care.
Thanks a lot.
Bye now.
Thank you.
Assalamu alaikum. Yeah.
Waalaikumsalam warahmatullah.